Welcome, everybody. Thank you for joining us in already our third webinar on InSAR. We do a different topic every time. This week we are talking about tunnel monitoring, and I think last time around we did a technical subject about time series. Very interesting. Some of that is coming back, but we try to keep a general introduction so that also the people that did not that were not able to attend last time can also still follow this around. So the title of this webinar is Tunnel Monitoring with InSAR, and it's part of SkyGeo Academy. And one of these parts of the academy is that we try to reach out to a lot of people. We have these webinars. We also do in-company or now over Zoom training. And if we do these webinars, there's a few options for people to participate. You can send some messages to us using the chat button that's in the bottom of your screen for the most people. And we have some people, actually Vincent, who you cannot see right now, but maybe can wave in the camera, who is our technical colleague who can also answer your questions on the chat. There's a Q&A module where you can send your questions and we can see them, we can answer them. Sometimes we pick a few of these questions to answer them actually in the webinar so that everybody can learn. Sometimes we try to answer them afterwards. It's depending a bit on the actual questions mostly. Some people also send in some questions beforehand, so Vincent will make sure we also answer these. Okay, so another thing is that we do these polls. I have now, and I think when you log in, you see one right away. And what you just do is click the buttons in which sector do you work. Well, I work in the industry, and rate your experience in InSAR. I work with InSAR, and then I press submit, and then the poll goes away. And when the poll's done, we try to also share with you the results. Try to use it in giving this webinar. Okay, so it's part of SkyGeo Academy, and the SkyGeo Academy has actually 4 pillars on which it stands: validate, visualize, apply, and discover. And in these, we try to explain InSAR because we know that InSAR is a bit harder to grasp than maybe some other techniques for measuring deformations. And one of the very first things you want to do is just validate the data that you get. So is this right? Another thing we try to address in these academy sessions is the visualization. How can you use our data to visualize the problem you have, or to visualize a sort of an alerting moment that you want to have? How can you apply this data to your actual day-to-day work? What should you do when you see certain effects in the data? And another part is discovering. We noticed that a lot of people discover just new phenomena based on our data sets. So, and with that, I will go to the next slide, and actually Freek will do that for me. Thank you, Freek. So I'm Martijn Houtpen, I'm a consultant at SkyGeo. One of the core lecturers together with Freek at the SkyGeo InSAR Academy. I've been doing this for about 3 years now. I work mostly in infrastructure, rail, and mining projects. So we try to, I try to delve from my own institutional memory also for this, some of the cases I will show. And I'm very happy to do this together with Freek. And Freek is our engineering manager, also one of the core lecturers, but he's also a researcher of InSAR technology at the TU Delft. And one of the most experienced people in the world, actually, you can find to talk about InSAR. So very welcome you are, Freek, that you join us. So today we will talk mostly about the time series product, and we have a whole product suite of Antares. It's deformation contour maps, time series products, coherence maps, change detection. I guess we won't go into the coherence or the change detection all that much today, maybe also not in the deformation contour maps, but we will go into some time series examples. But today it's not going to be very technical. I think at least for the cases that I will display, it's going to be more about applications and the type of problems people have and that they can solve or apply the InSAR data to. Okay, so with this, I will give the word to Freek as we look at the poll results. Do you want to talk about them, Freek, or shall I?
I can do this. That's fine. Yeah. Yeah.
Okay, thank you. Now, here's Freek.
Yeah, we will see Martijn back in a second. So, okay. So also welcome on my behalf. Thanks for filling in this poll. So we have a bit of an idea what our public is today. And the amount of people are still relatively limited, but those of you who are here are either from government or industry. And let's see how your experience in InSAR is so far. So at least every one of you at least heard or read something about InSAR already. So that's nice. So not completely new, but you may have read already something about InSAR, but maybe not in detail yet. So still, I think it's useful that today we go over a bit of the theory and behind the technique so that you can better understand the actual results and analysis that we will show you. Okay, let me start. Actually, I would like to start with the picture you see over here, which is a map of the Netherlands, and the country where SkyGeo, one of the offices of SkyGeo, is situated. And what you see in this image is, let's say, the surface motion expressed in millimeters per year. And in red, you see all the locations that go downwards with 5 millimeters per year. And you also see some blue patches that show an uplift of 5 millimeters per year. And all this has been measured from space by InSAR. And today we will explain you how that works. And of course, actually focus on the tunneling case, tunnel case today. Now, there's a lot happening around us, also in the Netherlands, and these are just a couple of examples of what kind of motion you can see in such an area. And you see here that different phenomena can cause surface motion. So, for instance, in the Netherlands, we have gas extraction, we have reclaimed land areas, so where used to be sea and now there's land. We have soft soils, so very old peat soils, for instance, that still show compaction. And also mining, for instance, can cause subsidence, either in production, in the production phase, but also still in case of abandoned mines, where, for instance, groundwater flow can still trigger some kind of ground motion. So a lot can be happening around us. This can be, let's say, due to natural causes, but also due to man-induced causes, of course. And the construction of a tunnel is one of these examples. Now, what can InSAR do? InSAR basically, in short, provides you a time series of surface motion or deformation, as we call it, on certain locations on the Earth. And you can see in the background picture that actually we can do this for many locations without installing any devices on the surface. And that's of course very interesting, because that means that we don't necessarily have to go somewhere or install things, but we can simply produce a product for an interested customer at a certain location around the Earth. And later on, we will show you as well what it means regarding available data sets and coverage around the Earth. So this is, in short, what we try to do. How do we do this? Basically, this is an impression what the system looks like. What we have is a satellite with a radar antenna on board that transmits a signal. And part of this signal is reflected back from the surface, and we capture this signal again at the satellite. And the result is typically a black and white picture, as you see here. And what is nice to see is that actually, whereas the picture you see a lot of clouds, but with radar we can actually look through the clouds, and it means that we can use every available image that we have for our analysis. So this is the input data that we use, and not only from one satellite, but currently there are many different satellite missions in operations. So we can use actually data from all kinds of suppliers of these data sets and pick the most convenient and most suitable data set for a particular project. And we can also do that for data in the past. I will get back to that as well. Now, I mentioned before, this is what happens. The radar signal is transmitted by the satellite, is reflected back on the surface, and is received at the satellite again. And the strength of this reflection is expressed in a grayscale, like you see here. So in case there's very low amount of backscatter of the signal, you see that as a black spot, because there's low intensity coming back to the satellite. So this is a lake. And you see also areas where the reflection is very strong or much stronger. And these appear in a white, let's call it the color. And this means that there's a very strong reflection from the radar signal. And particularly those ones are very useful for us to retrieve information on ground motion. But we do not directly use the intensity or amplitude signal. What we use is actually the phase information. So that means that the phase of the electromagnetic signal that has been transmitted. And what this looks like, if you have one acquisition of the SAR satellite, it looks like something like this. So I'm not sure whether you see anything here, but in principle, this is a purely random distribution or uniformly distribution of values between -pi and +pi. So some state of the sinusoidal wave, but in principle, these numbers are not interpretable. Now, what do we do in case of we want to measure deformation? We are not using one of those images, but we actually use two and maybe even more. But let's focus on the case of two of those acquisitions first. So what we have after a certain time, let's assume today we took a measurement and next week we take a measurement. Then in the meantime, something could happen at the surface, and this results in a longer travel path of the signal. So more of these waves, and we try to translate this extended range to a certain location to a deformation. That's the basic principle. So what we have is this. We have two sets of images, both with the amplitude and phase information. We neglect the amplitude, and basically we look at the difference between these two phase pictures, and then we start seeing a certain signal. Now, what you see in this picture is the result of an earthquake. You see many color cycles, so very strong surface motion, resulting in a lot of cycles of this phase, which we can translate to deformation at the surface. Now, this is the basic principle that we use to derive our products. But as I mentioned, we not only use two of those images, but basically what we do typically is we use all available images over a certain area. And this can be hundreds of images that are available. And based on this, we try to derive information. Now, again, a similar picture. What we do, and we have the situation of a transmitted signal. This travel path may become longer because of subsidence, for instance, and we try to measure this change. Now, there's a complication, and this is a bit of a technical topic, but still worth mentioning regarding also the case of tunnel construction. As we saw before, the only thing that we can actually measure are values between -pi and +pi. And that means that this distribution of measurements is obtained. So the values are between -pi and +pi. But as you can imagine in this case, this is not representing the true deformation. And the true deformation is more something like, for instance, this. So there's, in this case, a sort of gradually subsiding deformation going on, but we need to resolve this problem, to go from the original observations to the true deformation. Now, and what we need to do here is we need to make certain assumptions about the signal, especially about the smoothness of the signal, which can be both spatially as temporal. And typically we do this by assuming certain models, either again in space or in time. In this case, this is an example, of course, from a model in time. In this case, a linear deformation rate. And by analyzing the solutions that such a model gives, we can determine whether the solution we found is actually a reliable and sufficiently a solution with sufficient quality to work on. And it also means that the better we understand the physical phenomenon that we are studying, the better we can actually do this phase unwrapping. And so the more information we have, the better we can resolve this problem. Of course, without steering the solution to something that we pose to the problem. We don't want to force a certain solution. We still do sufficient statistical tests to determine the quality of the outcome, but somehow we have to direct the solution to get a good, reliable estimate. Now, this is what we do, and as I mentioned, the better we understand the problem, the better we can do this. But what can also be helpful is to use not only one model, but let's say a model composed of different components, so that we can actually derive the true deformation. Now, on this slide, you see a couple of examples, like a seasonal model or a breakpoint model. And also in case, for instance, of a tunnel construction, you may want to adapt your analysis with a certain model in mind to optimally estimate our deformations. So these are the basic principles, and this is what leads to a product like I showed you before. So many measurement locations, or points as we call them, with an associated deformation time series. I have a few more slides actually on the interpretation of these data, because this is also important for a proper use and interpretation. So first of all, what we can measure with InSAR are signals which are relative in time and in space. We are not able to provide absolute measurements. Such as measurements with respect to the center of mass of the Earth, for instance. But all what we provide are measurements which are relative in time and in space with respect to some reference. This may sound like a limitation, but actually this is in many, many cases, almost all cases, this is the thing that you're interested in anyway. So you're interested in the motion of a certain location with respect to the surroundings. So in case of a tunnel product, you're interested in the effect of this tunnel construction with respect to the surroundings, and not necessarily between that location and the other side of the Earth. That's not so important. It's about the local situation. So in many cases, this is certainly very good and sufficient information. Then sometimes also we get questions about what are you actually measuring? That's a good question, because typically with a geodetic or surveying techniques, you have a certain benchmark or a reflector, or you actually install a fixed measurement point. In the case of InSAR, this is not the case. These are, let's say, natural reflections from the terrain, and that's what we measure. So we don't know exactly very precise where that location is, maybe up to meter levels or sub-meter level. But what we do know is that every time when the satellite passes, we measure exactly the same location, so that we can actually derive this deformation time series. So these time series are very accurate and precise because we measure the same point. We only don't know that precise the actual location. And then also something useful for you to know is the effect of resolution. So I showed you a slide with different satellite systems and they have different resolutions. And this resolution also determines the amount of detail that we can provide in an InSAR data set. So in this graph, you see two different examples of resolution. In this case, a coarser resolution, here a finer resolution. And you can imagine that in case of a finer resolution, you're not only able to identify multiple good reflectors indicated by these big triangles, but also you have maybe less noise in your resolution cell. So it also improves the quality of your estimates. Actually, now we're at it. I actually see a question in the chat, maybe nice to discuss right away. A question from Chris about the reference points. And the question is, which reference point do you choose? That's a good question and a difficult question. And actually that is dependent on the project you're working on. Ideally we do this together with the customer, which knows their local situation best. Together with the customer, we can make a choice there. For instance, if it's known that a certain region has a very solid bedrock or a surface, then we can choose that. Or maybe we know a certain building or construction has a good foundation, we can do that. What is also possible is to actually use a larger region or even the mean of a whole data set as a reference. That can also be done. And depending on the particular products we discuss or propose the most optimal choice here. And an alternative is also to link it to other types of measurements. And I will say something about that later. Now we're at it. We actually get a second question. Now we're here of Anne asking, how do you know that you actually measure the same point every time? That's a good question, because I stated this, that we actually measure the same point. And we know this because we appear to be able to estimate a deformation time series with millimeter precision. So we can derive information at millimeter level. And you can imagine if we would not be measuring the same point, if we would be, for instance, 1 meter off, we would of course never be able to translate this to millimeter deformation. So the fact that we can estimate very precise a deformation time series proves that we are actually measuring the same points. Okay, these were some questions from your side. Thanks for that. Back to the topic of resolution. So this is the situation regarding resolution. And basically what it results in is, for instance, something like this. So here you see two examples of the same area somewhere in the world. And here you see the distribution of points, for instance, for the Sentinel satellite, and for instance, for the TerraStar-X satellite, which of course, the TerraStar-X satellite has a higher resolution, and that results also in a higher point density, and that makes you see more details. So you see more details in your product. And so depending on the project you're working on, this determines what is the most suitable satellite data set for your particular case. Okay, so back to the satellite missions. So what we see is that, as I mentioned, we have current satellite missions available, and we have satellite missions in the past. So we can make choices as we like, what is the most optimal configuration. And actually these satellites have a certain resolution and also a certain wavelength. And you see here L-band, C-band, X-band. X-band means the systems with the shortest wavelength, and they are also the most precise. Whereas, for instance, L-band has a longer wavelength. They have a smaller, worse precision, though they're less accurate or less precise, but they have other advantages. For instance, regarding the ability to measure a signal in case of some shallow or some vegetation, for instance. And what is nice, because these satellites are orbiting around the Earth, basically, is that we are capturing data all over the world. Here you see an example of available data of the Sentinel satellites. And this is a heat map of the number of available data sets. And you see, for instance, that there's the red patches have the highest density of observations, but you see that everywhere that there are large areas in the world with very high density of available data for the Sentinel, but also even if there's less coverage at certain parts, then still there's data available. So basically all over the world, we can do these kind of analysis. Okay, a few more slides from my part, and then I hand over to Martijn. And that's on the topic of integration. How do we see InSAR in the world of all other kinds of techniques? Now, basically, here you see a listing of all kinds of other geometric measurement techniques, for instance, leveling, GNSS, photogrammetry, etc., but also in situ measurements technique, extensometers, inclinometers, all that can provide information. And InSAR is actually one of those that can help you addressing a certain problem. And of course, these measurements can be integrated. What is good to know is how these different techniques relate. So here there's a graphic showing you a particular technique in relation to, let's say, the amount of time between measurements that you can reasonably obtain from also a cost point of view. So some measurements you can obtain every second or even faster, for instance, but others would be too expensive at that rate, and you'd only do once a year maybe. And the same holds for the distribution regarding point density in space. For some measurements you can do with a very high point density, for instance laser altimetry, but others you have a much coarser resolution of your measurements, simply because it would be too expensive to do it at the higher sampling rate. And of course each of these has a certain precision of the measurements. Now, basically, InSAR is somewhere in the middle of all these techniques, and it actually fills a gap between them. So that's why InSAR, in our opinion, is a very interesting technique to work with. And then my last slide is how does this relate to tunnel projects, where Martijn will show you examples about. Now, basically, you can raise the question, for which purposes can you actually use InSAR if you look into a tunnel project? Now you can actually translate this to different periods in the process. Basically what you have is you have the situation before the construction, during construction, and after construction. And for all these three phases, InSAR can play a role. For instance, before construction, you can do a historic analysis to know more about the natural behavior of a certain location. With all the other techniques that I mentioned, you need to start your measurements today to be able to draw a conclusion in a few years' time maybe. Because if you don't have measurements from the past, you don't have anything to analyze. Now with InSAR, because of these data sets that are available from the past, and the data sets are still in the archive, so we can analyze them anytime. We can actually look back in time, so we can tell you what has happened over the last 10 years, for instance, or even 20 years if you want. So that's what you can do. So during construction of a tunnel, you can of course look at, let's say, the area close to where the tunnel is constructed, or subsurface or at the surface. But it enables you also to look at a bit larger areas to see what is the effect of the tunnel on a bit wider environment, where you don't have maybe in situ measurements, because that would be too expensive to enlarge your area. And of course, it's interesting to integrate also InSAR with these techniques to link also these different phases together and to make use of the added value of the different techniques. And you can use InSAR after construction to see what the long-term effect is. So typically after construction, all the in situ measurements are stopped and you actually don't really know what's happening afterwards. But sometimes you are obliged, or you would like to know what happens afterwards. So also there InSAR can play a role. All right, this was my story. And I think there was also another question. Let me have a look.
Yeah, there was this question, and it was from Gokhan, and he said, "Have you ever compared results from X-band and C-band, especially for engineering structures? If yes, which one is more quality and more reliable?"
Yeah, that's a good question, Gokhan. Yeah, so indeed, so we very often, sometimes what we do is for a certain project, we analyze multiple data sets to get the most information that we can retrieve. And we do analysis with both X-band and C-band. And that's also useful because with more information you can do a better analysis. But in general, what you see is that with X-band, both because they have a shorter wavelength, so the precision of the measurements is better, and because typically the resolution of these systems is a little bit better, so you get also more points. So if possible, for such a project, you would in principle prefer X-band data, if you had to choose between the two. But I have to say there may also be a cost issue involved. So typically also X-band data is more expensive than C-band data, and that is more often, for instance, the original data may be freely available. So that helps a lot in reducing the costs. So in principle, X-band gives you a better product, but there may be an addition, more cost involved. So.
Yeah, and maybe sort of closely related to the costs. If you are going to use commercial data, you're also at least somewhat in charge of the way stuff is acquired. So you can configure. You have a bit more freedom than, for example, the open Sentinel data to configure a nice look angle or stuff like that. So that could be an added benefit.
Yeah.
Okay, thanks, Freek. I don't know if there are any other questions until this point, and maybe we will switch over presenting. I see another question coming up, and it's from Chris, and it said, "Could you also use InSAR to select the preferred area for building a tunnel?" You want to answer, Freek?
Yeah, I can say something about it. And you can add something to my answer as well, of course. So I think this is very much related to, let's say, this historic analysis I was talking about. So what InSAR can do for you is actually to make an analysis of actually a large area from what happened in the past 10, 20 years, basically. So it gives you a very good picture of, well, let's say, the normal natural behavior of a certain region. And of course, you would probably want to combine this with other types of data sets like geological information, etc. But certainly it could help you very much in selecting a certain trajectory for your tunnel. So I think, yes, this would be a very useful analysis to do prior to the actual selection of your site, if there's room for such a choice. Yeah.
Yeah, I can really imagine that as well, and especially if we're looking at cities with some buildings might be more stable than other buildings, which you might want to avoid, or stuff like that. In case of missing data gaps, we because you have the historic data, you can get a lot more information basically. And I don't think it will be the only one data source you will use, but it can certainly add to that. Yes. Okay, so if you stop sharing, then I will start sharing.
Oh, yeah.
Yeah, then I'll press the little button. Yes. And then I'll do this one. Yes. And I saw in somewhere coming in another question. Well, it was actually a great, useful answer, so that's good. Okay, thank you. Okay, so I try to sort of keep up to your proposed slides or to your slide, Freek, by going talking about three cases. One of the before, one more about what happens during the tunnel construction, and one about what happens after tunnel construction. And we start with before, just keep the natural order of things. And we are doing this project, and it's related to the Fastlanken tunnel in Gothenburg in Sweden, where we do actually the monitoring of the whole city. And you can see a picture here of part of this construction going on, and you can see in the back mostly here a lot of things going on along this highway. It is going to be a train tunnel, at least 6 kilometers. There's a few new stations being built, including one under the historic Haga Church, which I believe is a wooden church, really medieval structure. So it's very dear to the people of Gothenburg. So this is of course a very it's a tunnel. It's always a risky area if you're doing it under an urbanized area, and they have to deal with a lot of different soil types, a lot of switches between soil types, between bedrock and more clayey areas, and every time and they have to they pass into another soil type. They also have to change the way they excavate. They either do explosions or they do the boring of the tunnel. And this is in Sweden, so a lot of this is sort of a lot of the efforts they do in terms of monitoring is geared towards transparency and to actually showing the community, the people living around that, what are the risks that might occur to my old wooden house located here with these foundation poles? What are the risks to all the things that that happen in the city? And because they want to be very transparent about this, in part they also use InSAR. So what we provide to them, it looks like this. This is a whole map of the city, and you can see this trajectory going this way, and this is an above ground train. So this is sort of the trajectory. And we basically are monitoring this, have been monitoring this city for more than 3 years before they started the construction. And this way you can see what is the usual motion, like what Freek mentioned. You can do a whole analysis. What happens in a city like this? We use very high resolution, so you can see buildings being built, buildings demolished. You can see all kinds of deformations that already are existing in historic buildings, for example. They use this to set up a control program for the expected large-scale subsidence, which has to do with the groundwater sinking for the tunnel boring. They have actually reduced their leveling program from 6,000 leveling points to I think only 300, because they instead they are using InSAR to replace basically a large part of this leveling, so saving costs as well. And they use it to plan the geotechnical drilling. And every month they get an update and they get to see changes. So we really also detect where things are happening. And this is, I guess, now our 4th year. So they have actually started with the boring of the tunnels now. And now we get into a new phase of this project where you want to do monitoring during the actual activities. And it's also getting very interesting, because as these tunnels bore, they compensate by grouting and pouring concrete, making a concrete structure above them. And the amount of pressure that the tunnel bore, the TBM, gives is variable and also somewhat up to taste for people. And we can actually see that in some locations they are overcompensating, pushing the grouting, doing the grouting with too much pressure, and actually raising the surface on those locations, because there might be the pressure they expect downwards is a bit less than is actually happening. So they can, because they see this, they can also correct for this, which also saves them a lot of problems on top of the tunnel layers. Okay, so another case is more of what stuff you can do during tunnel construction, and actually it's not really about what you can do during tunnel construction, but it's more about what happened during tunnel construction in this case. So this is the A2 tunnel near Maastricht in the south of Netherlands. I think it's called the Prins Willem-Alexander, maybe even King Willem-Alexander tunnel. And it's quite a sight because you have two tunnels on top of each other, highway tunnels, and it goes through the city. This used to be actually a stop sign in the middle of the highway, and the highway crosses directly through Maastricht. Well, not anymore. You just pass under Maastricht, and you don't have to wait for the green light. While this tunnel was constructed, and it was in the period of 2011, 2014, there was some groundwater extraction to be able to construct the tunnel. And people who are living here just outside this picture on a hill have reported damages. And this is a large construction program. The reporting of damages can take very long. So there's a special commission in the Netherlands which actually handles these type of claims that have to do with groundwater extraction damages. It's called the ACSG. I will not translate it for you because I think it's a bunch of unusable or sort of ugly Dutch words. But it's the ACSG. They asked us to do a historical analysis to see so what happens before the whole construction. So the construction was in 2011, and what you can see, and this is on a very sharp -2 by +2 millimeter scale, is this street. So the tunnel is here. The pictures are obviously newer than the data itself, the background pictures. You see this street is actually where the damages happened, and already before construction, well before construction, 10 years before construction, you can see there was an increased movement locally to this street. If we go further in time, and this picks up a part of the construction, also still compared to the local surroundings, a bit more movement than you would assume to be normal. And then after construction, you can see that this still stands out as sort of a site that is moving a bit more than the surroundings. But what you could also say as well, okay, if I see this picture, I can sort of draw a circle like this, and this is the influence of the extraction of the groundwater, and it falls really neatly in this circle. So it might also be that it is related. So the judge is actually still out on that. The commission is still out on that. It's still an active case, I think. So we don't know also. I would say that because it's already, it's been happening for 15 years before the tunnel construction was already there. Yeah, it's maybe sort of due to a natural process. We don't know, but I think the importance here is that you actually have the opportunity to go back in time to see what happened during, but also before the tunnel construction happened. And this is obviously not something they did before they started construction, because then they would have really have the answer already ready at hand, or warned these people before they start the construction. Well, we can see your houses are moving. We are going to build a tunnel. And we assume this movement to continue. Yeah, in a way like that, communicate with them. Okay, so there's not really yeah.
We have actually a question on this from the audience.
Oh, that's good. I didn't see that one. Yeah, sure.
That's okay. So Gokan is asking, for this kind of project, which method do you use? PSI ? So did you use PSI indeed here?
Yeah, we did. Yeah. So these are all time series analysis, and all PS and DS InSAR for all of them. And you can see also, because we use different sensors, you can see sort of the different data densities, like you also mentioned in your in the part about resolution. This last one is obviously TerraSAR X compared to a RadarSat here, and I guess in a previous slide, an Envisat and an ERS, which are sort of comparable. Yeah, and they're all time series analysis. So, and though the differences are not really big between the street and the surroundings, I would say they sort of are at least particular. You would sort of, if you were to ask me where did the damage happen on this on all these pictures, we could sort of point to this whole street being anomalous to the rest, at least. Okay, so yeah, so that's the question done. And then after tunnel construction, so this is sort of a famous tunnel construction in the Netherlands, the North-South line, which is a metro going from the north of Amsterdam, being the central station, to the south, which is where the financial district of Amsterdam is. Amsterdam has historically always had a sort of a softish soil with a lot of different layers. The construction method is very complicated here with freezing parts of this sort of soft soil and building into that. And this is sort of a view of one of the stations. And I think this is at Rai, but I'm not sure because they all sort of look alike. And for this construction, they used two different types of tunnel boring. On some parts of the track, there's two tunnels next to each other. On some parts, it's two tunnels on top of each other. And if you sort of do a pre-analysis, what you expect for these tunnels, and you would also expect different types of settlements. So for the two on top of each other, you would expect sort of the first one to make a small trough, and then the second one even to have a sort of a smaller, deeper trough. This is also what we see in our data, and we also see that we do make an unwrapping error, which has to do with the modeling Freek mentioned. We consistently make this unwrapping error because in the first sort of period after the tunnel, the TBM passes the locations, you get a very sudden, very steep settlement, so these actually these black and blue ones, these are the actual corrected time series where we and these purple ones are still inclusive of this jump upwards, which is of course sort of a wrong unwrapping, and there are a lot of them on top of each other, which makes it a bit of an unclear image. But I have some more. I have a better image a bit later, a few slides after. So, and where the tunnel pipes are next to each other, you get a wider trough, less deep, basically. So it's less deep, but it's wider, or it's deep and it's smaller. And there also we have the same unwrapping error here, and we do, if we correct for it, we sort of match these predictions, which in itself is interesting, of course, and I do see a question about it. And it's from Ellie van Zee. It says, if you combine many time series, how can you maintain reliability? So this is sort of, so I think what we are doing here is not really combining them, but showing them all together. So we're showing them all together here as in a way to demonstrate that they all follow the same basic pattern. Basically, all these, and they correspond to, in this case, to these time series. They all follow the same pattern. So we use that to identify actually that we made a mistake, and that we consistently make the mistake at the same point in time. This allows us to correct for that. And if we, so this passing of this rail is noticeable. We saw it in the previous. We also, if you look at a single point here, you can see these points going up and then going downwards. As I mentioned, this is actually an unwrapping error. All these points should be positioned a bit more down here, actually. But what you also see is that this building, or this point, which is on top of a building, here has been stable for a few years, and afterwards it starts moving. And actually, if we visit that building 5 years later, we still see this movement continuing. So it stops, it passes, it sort of drops down, and here we can use the grayish dots to follow one ambiguity, so one error downwards. But still the movement continues here, and it might actually have sort of stabilized in the last part, but it still seems to, 5 years later, this building still seems to move. So this is a serious issue that happens after tunnel construction, where the normal monitoring would already have stopped for I think in this case, then the regular monitoring is 1 year after construction. So this monitoring stops for 4 years, and these people, their house in this time after the monitoring stops, their house moved about 1.5 centimeters still, and is probably still moving if we would look at it now. Okay, so this is what you sort of an example of the stuff you can see after tunnel construction. And with that, I would sort of like to wrap up, and I see that I did not edit this slide, so it still says time series, but it should say tunnels. I think like the sort of the main slide, actually, to the best slide for today to summarize this was this slide that Freek showed, which is this one. So what can we do with InSAR for tunnels? Actually, we can do, before construction, we can do a historic analysis. We can see what type of events happen during construction. We can do a whole forensic analysis. We can do combinations with in situ measurements, which we didn't show, but we can also do, and we also do that in Göteborg. And after the construction, we can do long-term monitoring to see these problems where people's houses are still moving 4 or 5 years after the fact. And with that, I would like to sort of conclude this session, and I'll skip really quickly. Sorry for this. One of my colleagues, maybe John, maybe Marianne, who's not in this call and whose photo I do not have, will call you for some feedback. And while you're looking at this beautiful picture of him, you get actually another poll, and I'll stop sharing my screen so we can talk about that. So the poll is actually about what we should talk about next. So we already did some InSAR introduction. We talked about time series. We talked about tunnels now. We can talk about a lot of other different stuff. So I would look forward to something about sinkholes myself, and coherence maps, and yeah, I'll just submit that and wait for you guys to submit as well. I want to thank Freek for his contribution.
You're
Thank
welcome.
you very much.
Next time.
Yes, very much until next time. Keep an eye on our LinkedIn and on our website. We will announce the next webinar. I'm not quite sure about the date yet.
I think
but,
in August somewhere.
I think it's somewhere in August, later in the summer holiday. Towards the end of the summer holiday, we will be back. Okay, thank you, Freek. Thank you all for attending, and I would say until the next time.
Bye bye.